So today we will be talking about the different loss functions of neural networks. Now this is not going to be a very big topic. The reason why is because the losses of the neural network are the same as the losses of machine learning. So if you have already covered these machine learning topics, then you already know about most of the losses that we are going to discuss today. But even then, let us go over this very briefly and explain and understand the different loss functions of neural network. Now, before we understand the loss functions, we should know that all these problems of neural networks or any problem statement per se is usually of two types. So you have regression problems and then you have classification problems. You can sort of differentiate classification problems into two again. You have binary classification and then you have multi-class classification. So we will be going over each of these problem statements and understanding each of their losses. So we will understand regression losses, we'll understand the different classification losses. Okay, so let us first start with the regression loss. So I'm just going to very briefly go over each of the topics. So we have mean square error, so what mean square error is, you have yi minus yi hat whole square. This is mean square error and you calculate the mean of this and you get mean square error. So this is the squared error. Error is basically the difference between the actual value and the predicted value. So you have the square of the error and you have to calculate the mean for all the data points. So that is mean square error. Then we have mean absolute error. It is the same as mean square error, but instead of doing the square part, we will be doing the absolute value. So now why do we need these two functions and how are they different? Well, first of all, mean square error is very bad when it comes to finding outliers. So it is not at all robust to outliers. In a way, like suppose you have a value that is way outside the data set or way different from the actual distribution of the data set. So in that case, if you will subtract the value, this is going to be a very large value, and then again if you square it, this is going to be a very huge loss. So it actually skews the actual loss. So that is why mean square error is not robust to outliers. So we have mean absolute error. Here, instead of squaring the error, we just find the difference, the absolute difference. So that is why this is robust to outliers. But then again, you have a problem with this also. What is the problem exactly? So the problem is when you have very small errors. So in that case, the problem is the value becomes very small and the model will not actually learn anything because the loss is going to be very small as is. Okay, so we need more different losses, right? Okay, so the next loss that we will be covering is the Hubbard loss. So Hubbard loss is basically a combination of both mean absolute error and mean square error, taking the best of both. So the Hubbard loss is equal to half of yi minus yi hat square when mod of yi minus yi hat is less than equal to a small value delta, and otherwise it is equal to delta times of yi minus yi hat minus delta square by 2. Okay, so this is the Hubbard loss. So what happens is if your error is very small, so at that case it will square the losses or the errors. So it will square the errors. So your loss will not be very small and it will penalize the loss, and as well as if the loss is very big, it will not do the square part of it, it will just use the absolute value. So you get the best of both mean absolute error and mean square error. here this is a graph of Hubbard laws for different deltas. So for smaller delta values, this is almost a flat line. So for smaller values it acts more as mean absolute error, and for larger values it acts more as mean square error. So you can actually decide what delta to choose, and you can then decide the amount of mean absolute error or mean square error you need for the function. Okay, so now let us talk about the problems that we can have with Hubbard laws. Well, the only problem actually is that deciding the value of delta. So it can be very daunting to decide what value of delta you should be using. So that is why Hubbard laws is not exactly a lot in use. Okay, so one last function that we will talk about, the loss function, is log cos h. So the reason why I am talking about this is because this is actually a good loss function, but it is not exactly used a lot. So the value is basically log of cos h of yi minus yi hat. Okay, so the reason why this is a good loss function is because for very small values, like, so I mean that for very small errors, so for small values of this function behaves like a squared function, square by 2. But for large values it behaves like an absolute function. So you don't even have to decide the value of the delta, it automatically does it for you. So that is why this is a good loss function. However, it is not used a lot. So we have completed the different regression loss functions. So let us go back once again. So what do we have? We have mean square error, mean absolute error, we have Hubbard loss, and we have log cos h. There is also one more, you might remember, root mean square error. It is the same as mean square error, but you just find the root value of it. So it is basically root of mean square error, that is root of 1 by n summation I equal to 1 to n yi minus yi hat whole square. Yeah, so this is root mean square error. This is also used. This is basically known as the L2 loss, and you have L1 loss, which is the mean absolute error, L1 loss. Yeah, I think you might have remembered all this, but we are just going for a revision. So okay, so the next that we are going to talk about are the different classification losses. Same thing, so we start with the easiest one. We have binary cross entropy. So what is the formula for binary cross entropy? So this is equal to minus 1 by n summation of I equal to 1 to n. So this is basically calculating the mean value of all the values or all the labels. So if you have yi log of yi hat plus 1 minus yi log of 1 minus yi hat. Okay, so this is the value for binary cross entropy. So I know it happens that when I started doing or learning this machine learning thing, I got very confused and it was very difficult to remember all the formulas. So one thing that I remembered was remembering what an entropy is. So for entropy it was yi log yi. Then we had cross entropy. Same thing, you had yi log of yi hat, and you have binary cross entropy now. So this is basically equal to yi log of yi hat plus 1 minus yi log of 1 minus yi hat. Alright. So next let us discuss about hinge loss. So hinge loss is basically maximum of 0, 1 minus yi hat yi. Okay, so here a different thing is, in most classification problems and especially binary classification problems, the labels are either 0 or 1, but for hinge loss the labels are minus 1 or 1. Okay, yeah, so how does this actually work? Think about this. Suppose your yi hat is very close to yi. Let's say both are 1. So in that case, what will happen? You will have maximum of 0 comma 1 minus, both are equal to 1, let's say. So 1 into 1, this will come as 1. So you will have maximum of 0 comma 1 minus 1, which is also 0. So maximum of 0 comma 0. So this will come to 0. So what that means is, if your actual predicted value is very close to the actual value, then your loss will be 0. In the same way, if you will think about this for minus 1 case, so you will have maximum of 0 comma 1 minus 1 into minus 1. So this will again come out to 1. So you will have maximum of 0 comma 1 minus 1. This will be equal to the same thing, maximum of 0 comma 0. So the loss is again 0. But for values that are close or that are very wrong, it will penalize a lot and you will get a loss of 1 in that case. So this is basically hinge loss. So these were the two types of classification loss for binary classification problems, right? So let us go and revise again. So this was classification loss but for binary. So we had binary cross entropy and we had hinge loss. Now we will discuss about classification problems, classification losses but for multi-class problems. It's the same thing, you don't have a lot of difference here as such. So instead of binary cross entropy, we have categorical cross entropy. Categorical cross entropy. So categorical cross entropy is basically summation of C equal to 1 to, let's just keep it I equal to 1 to C, where C is the number of classes basically, and you have yi log of yi hat. This is for one value. So this gives out, let's say you have there is one actual value you will have. Let's say you have 3 classifications: dog, cat and rabbit. So for suppose the actual problem is a dog, so yi is 1 for dog and others you have 0, and yi hat is the predicted value. So you will have, let's say, 0.8 for dog, 0.1 for cat and 0.1 for rabbit. So then you will calculate all of these together, and this is for one data point, and then again you will summation all of this for the number of data points. Okay, but let's be clear. So it's basically for one data point, yi log of yi hat. So this is categorical cross entropy, right? And we have one more, and this is known as KL divergence. So you need to understand, the thing is, this is used when you have two very different distributions and you need to find the difference between the distributions. Like you have a uniform distribution here, you have a binomial distribution here. So you need to actually understand or find out how different each distribution is from the other, right? In that case we use KL divergence. So the formula is pretty much like this. So you don't have to actually understand the whole thing right now. We will go over this later on. So what this means is log of px minus log of qx. So this can be minus, this can be division, because it's the log function, so you can do both together. So basically KL divergence is used in generative models. So to find the difference between two different probabilities or two different distributions, you need KL divergence. There are a lot of other things. You have KL, you have JS divergence, you have earth movers divergence, you have a lot of different stuff. But yeah, these are mostly used for generative models. So let's say you have variational autoencoders or you have GANs and stuff. So these are basically used for deepfakes. We will go over the architecture later on, but yes, so these are basically used for these type of problems. Okay, so let us revise now everything just once and for all. So we had regression, and in regression we had mean square error, mean absolute error, and we had root mean square error, Hubbard loss, and log cos h, right? So these were some of the things, and root mean square error is known as L2 loss. L1 loss is basically mean absolute error. Then we had classification losses, we had binary cross entropy, we had hinge loss. And then now after binary classification we have multi-class classification, we have categorical cross entropy, and we have KL divergence. Now there are a lot more different kind of losses, but these are the most commonly used losses. So what I would suggest is to go over this block. So it describes a lot of other losses that I have not gone over, so you can go over that and understand everything. So the link will be there given to you. That's it. Enjoy your day and have a good learning.